encoded. This state that Mangesh is showing here, this cannot, you cannot really get it from any alpha prime going to infinity limit from the tensile spectra. This is a new feature.
Yeah. Okay, thank you.
Okay, so yeah, so let's thanks Mangesh. So we have the next speaker, Aritra, and he is going to speak about tensionless tails, Rindler road to Carolean worldsheets.
Okay, let me.
So Aritra, yeah, please share this.
Share my screen. Screen. Is this visible?
Yeah.
And is my
so
cursor?
You have 30 minutes, so 25 for presentation and 5 minutes for discussion. So I'll give you a reminder.
Is my cursor visible?
Yes, yes.
Okay. Okay. So yeah. So thank you. Thank you, the organizers, for inviting me to give this talk, and thank you, Mangesh, actually, for giving very nice introduction to this. Whenever I try to talk about these things, it seems that the introduction takes all of the time, and actual meat of these things are never never addressed. So this is something that we have been talking about for last couple of years, and these are the papers that these are based on. Something that we wrote last year, and we recently sort of started to understand it more, or that's a misnomer. I mean, we started to get confused more about this, and we wrote something else recently. So yeah, so this is what I'm gonna talk about. So as Mangesh was they're telling you guys that these tensionless or null strings, they can be thought of as fundamental objects, as you are showing you this null action, or some sort of limit on the tensile worldsheet theory. And it seems it happens to be that these limit of this of the theory is a Carolean limit on the worldsheet. What I mean by Carolean is the worldsheet speed of light actually goes to 0, as opposed to the non-relativistic limit or the Newtonian limit of the usual theory. So there are two ways to look at this theory in this case. So what I would be telling you about is a bit more wacky than that, and I will be telling you that these limits can also be interpreted as some infinitely accelerated worldsheet limit. So this tension going to 0 limit actually correspond to some sort of infinite Rindler acceleration, and when you go to the infinite limit there, that also generates BMS3 as the worldsheet residual symmetry algebra. Now,
Aritra, can you go to the full screen mode?
Yeah, I can go to the full screen mode, but somehow I cannot handle. Somehow just a second, my Zoom is doing something weird. Let me just, yeah. So okay, sorry. How do I get rid of the Zoom window? Okay. Cannot seem to get rid of the Zoom window. Okay. Is this fine? With full screen?
Yeah, it's fine.
Okay, nice. So yeah, as I was telling you guys, so these null strings are generated by this infinite worldsheet boost limit, where you effectively take sigma going to sigma and tau going to epsilon tau, and where this epsilon actually goes to 0. I will actually violate causality and sometimes refer to Mangesh's talk. If you are tuning in just now, I'm so sorry. So the tensionless oscillators that Mangesh was also talking about, the C's and C tildes, they needed to be some sort of combinations of A and B, so that you can put them into the oscillator form, usual tensile string oscillator form, if you wish. What Mangesh did not tell you, that if you go from the limiting perspective, in the Carolean limit, you can actually imply a relation between these ANs and BNs, which actually appeared in the tensionless string mode expansion. They are related to the alphas and alpha tildes in the tensile string in certain way. So once you have that, and you know that the worldsheet metric actually degenerates at the strict epsilon equals to 0 limit, and the Riemannian structures stop making sense, and you have to inherently do something Carolian to make sense out of the theory, you can actually proceed. What you can see is that as again, quantizing these null strings, they require a consistent choice of vacua. You have different vacua, you have to impose your constraints, and that actually defines your theory. Now, for convenience, I have written the mode expansions like this form, where the C's and C tildes appear instead of these A's and B's that Mangesh was telling you about. And the oscillator representation of the vacua is particularly like the highest rate vacua of the highest rate vacua of the tensile theory, but in terms of the C's and C tildes. Now, what is very interesting? Yeah.
So these oscillators, when you're talking about oscillators, you usually think of them as oscillating in time. So there's no time dependence in the exponent. There's just sigma. So in what sense are they oscillators?
They are oscillators in terms of canonical convolution relations. So for example, these A's and B's that Mangesh was talking about, these were like X's and P's, and the CNs and CN tildes are certain combinations of them, so that they are like your annihilation and creation, a couple of annihilation and creation operators.
Yeah, they are creation and annihilation operators, I agree. But in what I'm confused about is in what sense is it legitimate to call them oscillators? Maybe it's just semantics or
yeah, I mean, by all means, I mean, it's we can call them something else, but I when I say oscillator, I am just talking about just the algebra. I mean, of course, I understand your question that, but as you can see from this mode expansion, a tau going to something at a small tau limit has been taken on this oscillator, so that the tau dependent oscillator, the tau dependent exponential is gone.
Yeah. Okay.
Right? Yeah. So what is new that if you take these earlier definitions of C's, and if you put in those definitions of A's and B's in terms of the epsilons, you find something very, very interesting, that the tensionless oscillators C's, they are related to the original tensile oscillators in a nice way. And you can actually write this transformation in terms of some Bogoliubov transformation, where the Bogoliubov coefficients cos A theta and sin A theta are given by these epsilon dependent factors. And it turns out that these remain Bogoliubov transformations in the whole flow, starting from the tensile theories to the tensionless theories. Basically, if you put epsilon equals to 1, where there was no boost to start with, of course, you get back alphas and alpha tildes. In between, when the boost was finite, of course, nothing changes, because boost does not actually, until the infinite case, boost actually doesn't change the system. Only at epsilon equals to 1, things change and new things appear. So now you can see that there is some sort of interpolating definition around here, which is more than just a boost. It seems that there is some sort of physics of acceleration going on somewhere, which is giving me this sort of structure when I actually go to the epsilon going to 0 limit, where singular things appear. So that actually made us think that that there must be something, this 0 alpha to 0 C, which we call, like the tensile to tensionless vacuum. This suggests that there is a flow which is more than a boosted system, and this explicitly appears in this UR contraction, or the Carolian limit, because the modes, when you do the Wigner contraction of the generators, the modes in that actually mix with each other. The n's and minus n mixes, and that's why this Bogoliubov transformations appear. Now, if people do and the non-relativistic construction as well, but in the non-relative construction there is no such mixing. So although classically both of them actually lead to the same brackets because of the isomorphism between two-dimensional GCA and BMS3, but they are physically very different objects. Now, since we were thinking about whether acceleration can also produce some null theories on the worldsheet. So recently we found out that if you have strings world sheets near horizons, then they can also be seen to be becoming tensionless. So actually, a near horizon limit on a black hole is basically a Carolean limit. So this is a work by Laura and the collaborators. So basically what they did, they showed that the C going to 0 limit actually corresponds to going near the horizon in some particular parameterization of the metric called the Randers-Papp through formalism. But since there is already a Carolean object present in the background, so you can actually think about induced metrics on closed strings near, let's say, a Schwarzschild black hole horizon, and taking near horizon limit on the worldsheet with some tortoise coordinates, some mumbo jumbo there. What you find out is that when you put everything back into the Polyakov action, the action tells you that the tension has scaled, and it has scaled with this exponential of RC factor in this box, where this RC going to minus infinity actually is the near horizon limit. So when the worldsheet actually moves very close to the horizon, the string also becomes tensionless. So what we understood from this, that since near horizon limit on the black hole is a Carolean limit, and the Carolean limit on the background is a Carolean limit on the worldsheet as well, because the tensionless limit itself was a relativistic or a Carolean limit. This actually settles a very important question, because there has been this idea that a Carol string, one with a Carol, which is moving in a Carol background, and a string with a Carol worldsheet, something which is inherently Carol on the worldsheet, they are different things. But our claim is that once you have a Carolean background, you inherently have a Carolean string as well. So since this works, the next step was to, since of course black holes are hard things to work with, we thought since near horizon of black hole can be locally replaced by some Rindler space, why don't we start to try to see what happens if I have a string on the Rindler on a explicitly Rindler space as well. Now, bear in mind that this realization came in two steps. In our first paper, we talked about only worldsheet which had some inherent Rindler structure, but in the recent paper, we have some understanding of it from a Rindler target space point of view as well. Just to remind you, this was how the Rindler coordinates worked. You had your Rindler times, which were these lines here, this eta1, eta2, eta3, etc., and of course you had your particles would move in this hyperbolas given by some coordinate xi, and you had right wedges and left wedges and whatnot. So a nice thing to see here is that the Rindler horizons are at let's say in this metric here, the metric that I have written, the Rindler horizon sit at x0 going to infinity and x1 going to minus infinity, etc. If you look at some induced metric in the closed string induced metric in this background, what you find is that this actually keeps conformal gauge on the worldsheet invariant, but there is a factor sitting out on outside, which is like e to the power 2x1, which actually goes to 0 when you go near the horizon. So the whole worldsheet actually degenerates, which is one of the telltale signs of a null string appearing in the theory. So what we decoded out of this, that the background Rindler structure actually induces some sort of a worldsheet Rindler structure. Of course, worldsheet coordinates are, you could say that I can do some wild transformation and make it flat as well. But when you are near the horizon where your conformal factor actually goes to 0, then you cannot really do that. So null strings actually would emerge when the horizon is hit in some way. And also this would, yep.
So in the previous talk, I understood that in this tensionless limit, the worldsheet action reduces to x mu dot. Is that correct?
Yes, in one.
So now you're saying that the entire worldsheet action degenerates. In what sense are those two?
Okay, that's a very good question. As you were seeing in the other talk, that the dot square survives. Now the problem with this formalism is that it does not really care about when or how your metric actually degenerated. You could have both G tau tau and G sigma sigma going to 0, or you could have the G tau tau going to 0, and that would not really matter. But in any case, if you have null induced metric structure, then you could always do this formalism. Now, that I would say that is a bit of a cheating on my part, that I am not exactly talking about a Carolean structure where you would actually have the G tau tau part that would remain, and that would go away. But it seems that, since again it's a two-dimensional thing, for example, when I was talking about this induced metric near horizon, you would see that, at r equals to 2m, the induced metric basically vanishes. But you can still talk about null strings at that point of time. But this is just another way of looking at it. I'm not saying that this is the exactly same way.
So what exactly do you mean by null strings?
I mean, when I say null strings, I mean that the worldsheet metric of the string at every point on the worldsheet has degenerated.
But that would mean that the action goes to 0.
What?
Why wouldn't that mean that the action goes to 0?
The action goes to 0.
Yeah, if the worldsheet metric degenerates, what do you mean by degenerates?
Determinant of G going to 0. That's why you cannot write the metric the action as root minus G alpha beta del alpha x del beta x anymore.
Yeah, so if the determinant goes to 0,
yes, that's why exactly. That's why you would have to do this other formalism that Mangesh talked about. That's the LST formalism, where you change instead of these G alpha betas, you have these one forms that you put into your action and write down, so that actually encodes that null structure. That's
even
how
there it's basically the Wiederbine formalism, right? You're going from the metric formalism to the Wiederbine formalism in some sense, right? So even there you would have the determinant of the Wiederbines.
Yeah, you would have that.
So if the determinant of the metric goes to 0, the determinant of the Wiederbines would also go to 0 in one sense.
I mean, not.
So even in that formalism also, I suppose the thing would degenerate in the same sets as the previous formalism.
Yes, but then as I was telling you, that these Wiederbines are not the Wiederbines that these are Carolean Wiederbines, where you cannot really do the up and down because the metric has degenerated.
Sorry, Aritra, I think we need to move on. And just a small comment that, so I think it's better to interpret it in terms of the vector density, right? I mean,
right. I mean, yeah,
and a particular choice of these gates. Sorry. So yeah, it takes that form, this x dot square.
Right, but in general, you can have any two component vector density that would give you a null metric as well.
Right.
I can tell you. Sorry, I can talk about this in the discussion session if you want. Okay. So yeah, as I was telling you, so the idea of this embedding is that anywhere where you have put in put the string in some sort of accelerated background due to this embedding, there would be null points which will exist on the worldsheet where the metric has degenerated because of this the particular nature of this embedding. So now, what do I mean by a Rindler worldsheet? Because of course, I have been talking about Rindler background, but what do I mean by Rindler worldsheet is a bit more involved. So how we interpret a Rindler worldsheet is a generalization of a Rindler world line, which is basically a hyperboloid. Now, instead of to get these strings, usually you do the constant time slices. Instead of usual tau time slices, you will have eta time slices, the Rindler time slices basically. So these hyperboloids, as you move towards the more and more accelerated region, the throat of the hyperboloid will start to close, and you will get just something like a null cone. That's how we interpret the features of a Rindler worldsheet. And the good thing about this is as you increase your eta, as you go towards the null lines, the constant time slice is actually to start to become elongated, and at the end you just have the null line. So basically just a one null line. So this is our picture of the Rindler worldsheet. Now it comes from that when I try to talk about these strings in a Rindler background itself, it implies basically that from go from an inertial and a non-inertial worldsheet, which is, inertial worldsheet is things that we know, and non-inertial worldsheet was just what the pictures that I was showing you. They need to have some sort of a map between these two. And it turns out that there are these maps, these sigma and tau, going to xi and eta maps, and which are basically singular at certain points. And this actually marks the special points on a Rindler worldsheet where the induced metric has degenerated and has to be taken care of very carefully. This is not something new. I mean, you have a string where there are particular points where the worldsheet embedding has it is not valid anymore, and these are particular null points. This is not new. This is like a folded string, which is there in the literature. For example, in the ADS case, you have these GKP strings where strings are folded at certain points, and in a sense they could be thought of as open strings bound together by closed string boundary conditions. So in our interpretation, we could think of these accelerated closed strings as some sort of open string segments. I mean, there could be more than one segment, of course. I mean, more than two segments, of course. And these are glued by some sort of boundary conditions, which still make them closed, but under quotations. So if that works, sorry, I have been going on. I mean, I hope people have, do people have questions? Sorry. Okay, then.
We have 9 minutes, so.
Oh, sorry. Okay. Then I should really fly. So as I was telling you, so once you can have that. So you have you could have what I showed you, this map is basically in the what you would call in the flat Rindler, in the flat space case as the maps on the right Rindler wedge, and there will be other maps with the minus signs, which you will call the left Rindler wedge. What they mean, I'll come to that, but for now let's just think that you had some non-inertial worldsheet, and as long as I'm not hitting the horizon, I am in a finite acceleration phase, my symmetry generators will be changed. I mean, it's very easy to find those generators, and it turns out that these still at finite A will give you the classical part of the Virasoro algebra, or the Witt algebra, if you please. And as I was telling you, since there are two maps on the worldsheet that you can do, seems that there will be another class of the worldsheets where you would have some other generators of the Virasoro algebra, but they are related to each other by these flipped transformations where this n goes to minus n. So this is what basically is sort of an analytical continuation between the right wedge of the Rindler string to the left wedge of the Rindler string, because you can see that the direction of the time lag killing vector actually changes. So once you have that, you can also talk about what happens at the acceleration going to infinity limit. Now, of course, this is all worldsheet point of view, and you could see that there are two ways to take this limit. In the one case, you could just combine objects from the right wedge, and in the other case, you can combine objects from the both right and left wedge. It turns out that in the first case, it is like an BMS or the conformal Carolean sort of algebra, and the other case, it is the Galilean conformal algebra. But both of them are classically the same, so you would say that at the acceleration tends to infinity limit, I still have the BMS algebra. Now, what this all means is in terms of this nice geometric picture, which I hope to. So basically, as I was telling you, these Rindler worldsheet can be thought about some sort of hyperboloid, where you have the closed strings, quote unquote closed strings. They are basically constant eta, constant Rindler time slices of your original wall, or of this hyperboloid. And if you I don't know if you can see the picture whole. So I have drawn like two different slices of this hyperboloidal world sheet. One along, let's say, some eta direction and some minus eta direction. So what happens is that if you look at the right Rindler wedge and the right Rindler map and the left Rindler map, they can only cover either this green-red segment of this picture, or the blue-yellow segment of this picture. So that actually gives you a sense of right string and a left string. So these are all the quote unquote closed string will be sitting on the constant eta surface, but you will have a particular string which you will call, which will be like the right modes of the Rindler scalar, or and the left modes of the Rindler scalar. And these two ways to combine the string to make it a whole closed string sort of, that actually would correspond to the two ways to construct the algebra that I was showing you. And they are all connected at these points, which are these special points, null points, or the folding. Excuse me. So if you have that, you can go ahead and try to quantize it, and you will find out that since we are talking about two disconnected segments, now the vacua is basically some sort of direct product of this right and left vacua. But since you can still write string modes which are valid over the whole thing. But of course, these beta n's and beta l's, they don't really talk to each other because they sit on causally disconnected segments. And
sorry, Aritra, you have 5 minutes including question and answer. So
okay. Can I have like 2-3 more minutes?
Okay. Yeah.
Okay. So this so sorry.
No problem. Yeah, please go ahead.
Yeah. So these UN modes are positive eigenmodes, and so the question is that likewise in the case of Rindler scalar fields in Rindler, how would you define your global modes? And it turns out that it's once you understand that green red, this right, what is the right Rindler string and what is the left Rindler string, doing that is analogous to the usual scalar field case. And you can analytically extend the modes and define globally well-defined ones, and you can check their orthonormality and all sorts of things and write down mode expansions. What this does is that it lets you write these Bogoliov transformations between tensile strings and these beta R and beta L oscillators that I have been talking about. And in the limit, when you take the acceleration going to infinity, you will find that these are connected to each other via this map, that the epsilon goes like 1/a. That is to say, highly accelerated strings and highly boosted strings, they converge to become the same sort of null string. Again, I think so. Okay. The other thing is that if you try to talk about what the gluing conditions or the boundary conditions that actually keep them together, you find that the state that on which that I'll talk about when I try to glue these states is basically something like a coherent state of these betas and beta deltas. And in the acceleration going to infinity limit, you just have a boundary state along all directions, and that is what you basically get from null strings in the extreme boost limit. So what this all tells us that the appearance so since we have this boundary state, and we have been calling interpreting this as a long open string in our earlier papers. So what we have a way to talk about worldsheet Unruh effect, which is like basically folded string, folding of the strings, and these casually disconnected segments, they couple it together in the accelerator string Hamiltonian. Why do I keep calling them closed? Because they are, one of them, of course, they are, you can call them like closed entangled objects, and these level matching conditions on these connected, this connected worldsheet actually remain invariant throughout this flow of acceleration. What I don't have much time. I think I should end. I mean, this is something that I've been trying to talk about, but let's not do that. What I was now, whatever I was telling you about are like Rindler strings these are not real black hole horizons. So we should be careful about what we call a horizon and what we would not. The right thing to do would be have inherent Carroll structures, Carroll target spaces, and couple Carroll background, Carroll worldsheet to it directly to see how these things work. And of course, since I got these entangled strings, left-right entangled strings, so it would be nice to have an idea what they actually mean. Also about Hagedorn transitions, it seems that there are kind of connected objects that appear in, let's say, this 𝗲𝗫𝗀𝗀 picture. But of course, it's not clear how to get, let's say, the Hagedorn temperature in our picture. Sorry. I think I don't want to say anymore. Yeah, that's all.
Yeah, thanks, Aritra. So, questions?
Yeah, I think the last part was too fast.
Okay, Shamdatta has a question. Yeah, please.
Yeah, so these strings, so are you saying that when ordinary strings approach the black hole horizon, they become Carolian strings or something like that?
Yes, that's the idea, that when you have a Carolian background, that actually induces a Carolian structure on a string worldsheet.
And that's because of the metric in because of the space-time metric in the worldsheet action.
Because of the
behavior of the space-time.
The embedding of the space-time. Yes.
Yeah. So.
Which is also probably I don't know, but people who do like holographic QGP and stuff, I think they also deal with strings where horizons are induced from background and these strings hit up basically. So of course, I mean, those are probably probe strings on open strings, but yeah, something similar.
So can you kind of envisage a sort of stringy hair on black hole horizons?
Oh, I'm not qualified enough to make a comment on this. Sorry.
Okay, so there is a question from ICTS.
Hi.
Yeah. So yeah, ICTS raised hand. So
I am audible.
Yeah, you're audible.
Hi, like, was there a similar story about like when I study strings in like say flat space time, say in an appropriate dimension, would it induce some BMS structure on the string? On a flat space time dimension. On a flat space time. Yeah, I'm studying strings on asymptotical flat space times, and the have the BMS structure, but that doesn't there's no usual story of that inducing something similar on the worldsheet, right?
Okay. So I basically take my string to sky plus or something like that. Is that the idea? Yeah, I mean, I thought that was the idea here, right? Here, but since it was a horizon jump near horizon, it had some Carolian symmetry. You say that kind of gives so many properties, that kind of induces these properties onto the worldsheet theory, right? I'm Carolian symmetry of the space-time inducing Carolian symmetry on the worldsheet. I'm asking a similar paradigm, like should I expect something similar for BMS symmetries of the asymptotia? Like, so basically, I mean, yeah, okay, I understand.
Can I jump in? I think the BMS symmetries are not inherent in the metric, which is what did the thing for the Carolian string. So the BMS symmetries.
No, that actually does not work in the same way. So I mean, I guess the point is that if you were to think of about the whole thing in as strings propagating only on scry plus or I mean scry minus, with the null direction being your time direction, we would expect the same thing to happen there as well. So yes, I mean, if you have a string on a null surface, if you have a strings propagating in a null background, you'd expect that similar things are induced on the world sheet as well. But it's not strings propagating in flat space, right? It's strings propagating on Scri+, if you wish.
So you're talking about the sort of metric which Laura had in her talk, the full metric in the asymptotically.
Yeah. I mean, if you think about the metric on Scri+, it's 0 times du, right? I mean, 0 times du squared plus rest. So I mean, if that is what you take as your space time, then yes, the same things. At least I would expect that they would go through.
Okay, is there any other question from ICTS? Because I see the hand is still raised.
Just confirming. So why is like in any closed string propagating near the bound near the Scri+ would have these properties? So why do I not have to discuss these when I naively discuss string scattering amplitudes or something?
That's a good question, which I do not have an answer to. I mean, I think that's
yeah.
I mean, I guess we don't necessarily look at I mean, asymptotic symmetries when we are discussing scattering of strings at the end, right? I mean, I don't know how to pose the question actually. If somebody somebody more qualified should actually try and phrase this for us. But I mean, what I'm trying to say is that if you were to think about Scri+ essentially as the space-time in which you should actually propagate your strings, then similar structures should show up there as well. I mean, it's not propagating in flat space. It's propagating on the null boundary of flat space, basically.
Arjun, can I just say something? So
yeah, please.
Yeah, no, I mean, for at least one of the quantizations that we were discussing, that the null string gives you the ambitwister string, and for the ambitwister string amplitude, we know BMS is present because you have word identities which give you the soft theorems in the ambitwister string amplitude. So that kind of confirms the. I mean, it's the answer. I would think the answer to the previous question is yes. That I mean, that there may be some.
That's a good. I mean, that's a good point. Yeah, I mean, that's true actually. Yeah.
Yeah, for the ambitwister case, I guess it's true because of the I think ambitwister string is much more well studied. But my only problem is that the quantization that we are talking about here, it's not the ambitwister quantization. It's
yes, that is true.
More like a thermal.
But close to Scri, because there's a possibility you could.
Right.
Yeah, hopefully the same things, similar things would show up essentially.
As long as you can write a target space metric in terms of a generic Carroll metric, I think this goes through.
But yeah, I mean, I think the question regarding why we do not think about string scattering and why don't these structures show up there is.
Don't people talk about string scattering around Scri+? Because I thought that's what, I mean, Alok can probably.
Yes. So he's saying that one of those things, yeah.
I mean, right?
Okay,
Hello?
maybe. Oh, hello.
Yeah, maybe we can postpone to the discussion.
For the discussion session. So next.
Hello.
Yeah. Hello. Yes.
So like I from what I understood from what Alok said, it's just recovering the usual BMS and the usual soft theorem kind of stuff from string scattering amplitudes, right?
From the ambitwister, I mean, which is not which is kind of singular limit of the tensile string. I mean, it has only finite number of massless states, but for those ambitwister string amplitude, we do see BMS.
Just the flat space soft theorem kind of.
I agree. Yeah. That's true.
The point of what these guys are doing is that like you have to carefully take a deformed limit on the world sheet and so on to see this.
Yeah. So there also the BMS is on the world. I mean, the symmetry is acting on the ambitwister world sheet. Right. I mean, you have the vertex operators on the world sheet there, which implement this super rotation and super translation, right? These charges are defined on the world sheet.
Yes.
So,
But you don't have to do some very careful world sheet analysis with the scaling and so on to see it.
Yeah,
well, I mean, that's a point that I mean, if you do MB twister, then it's already there. And if you go from null string perspective, at least there's one quantization, as Mangesh was discussing, which gives you MB twister.
Exactly.
So what happens is in that case, you take the full. I mean, the BMS actually reduces to just one half of a CFT, and then trying to understand vertex operators and things like that are I mean that's just the usual stuff, right? But for the rest of them, it is not, because the whole whole structure is there, and one needs to do more work, and hopefully similar things show up as well.